On a Tuesday morning in late May 2025, Avi Loeb sits before a camera and delivers a number that will reverberate through astronomy for months to come. 6 out of 10. That is his assessment. A 60% probability that the object designated 3I Atlas is not natural, not a comet, not an asteroid, technology. The object had been discovered weeks earlier by the Atlas Survey System in Hawaii, the same network that tracks near-Earth asteroids and watches for anything unusual crossing our cosmic neighborhood. But 3I Atlas was not near Earth. It came from somewhere else entirely. The third confirmed interstellar object ever detected, following 1I Oumuamua in 2017 and 2I Borisov in 2019. Both of those visitors sparked debate. Neither carried a 60% technology rating from one of Harvard's most prominent astrophysicists. Loeb does not make this claim lightly. He has spent years arguing that Oumuamua's Strandny acceleration and elongated shape suggested artificial origins, enduring ridicule from colleagues who insisted it was merely an unusual comet. Now with 3I Atlas, he has data that troubles him far more deeply. The trajectory is wrong. The chemistry is impossible. The timing raises questions that natural explanations struggle to answer. The data doesn't fit the models. Within hours of Loeb's statement, observatories around the globe begin redirecting their instruments. The James Webb Space Telescope, already scheduled for a brief observation window, moves 3I Atlas higher on its priority list. The Very Large Telescope in Chile adjusts its mirrors. Gemini South prepares spectroscopic analysis. Even amateur astronomers, armed with backyard telescopes and CCD cameras, start hunting for the visitor in the pre-dawn sky. Because if Loeb is right, if the probability truly sits at 60%, then humanity is not simply observing a wandering chunk of ice and rock. We are watching something that was designed, something that was sent. And that possibility, however unsettling, demands investigation. The object itself appears unremarkable in initial photographs, a faint smudge of light moving against the background stars, barely distinguishable from countless other celestial objects catalogued each night. Its brightness fluctuates slightly, suggesting rotation. Its motion is swift, traveling at approximately 137,000 miles per hour relative to the Sun. Fast, but not unprecedented for an interstellar visitor. Oumuamua moved faster, but Oumuamua did not exhibit what 3I Atlas exhibits. On August 6, 2025, the James Webb Space Telescope captures its first detailed spectrum of the object. The instrument, positioned at the second Lagrange point nearly 1 million miles from Earth, splits the light from 3I Atlas into its component wavelengths. What it finds is startling. The plume of gas surrounding the object contains 95% carbon dioxide, only 5% water vapor. This ratio is inverted from what comets typically display. Water ice, the dominant component of nearly every comet ever studied, should produce plumes rich in H2O. Carbon dioxide exists in comets but as a minor constituent. Here, the chemistry is backward. Like finding smoke without fire, astronomers later remark. The molecules are there, but the proportions make no sense. The JWST team, led by principal investigator Martin Cordiner, releases preliminary findings cautiously. They note the unusual composition. They suggest possible explanations involving carbon dioxide ice deposits that survived the journey through interstellar space. They do not speculate on artificial origins, not publicly, but the data circulates among researchers and the questions begin to accumulate. Why would an interstellar object carry so much carbon dioxide? Where did it form? What conditions in another star system would produce such chemistry? And why, if this is merely a comet, does its gas output not match the signature of any comet in our own solar system's history? Every answer opens a bigger question. By September, amateur astronomers provide the next surprise. On September 7th, a photographer in Arizona captures an image of 3I Atlas that spreads rapidly across social media and astronomy forums. The object appears distinctly green in the photograph, not the usual white or pale blue of cometary comas, but a vivid, almost artificial-looking green glow. The color is striking. Unnatural, some say. Others argue it is merely diatomic carbon, a molecule known to produce green emissions when ionized by solar ultraviolet radiation. But the intensity troubles some observers. The green is too vivid, too concentrated. Comets can appear greenish, yes, but typically the color is diffuse and faint. This looks almost like a filter has been applied. The photographer insists the image is unprocessed. Other amateurs replicate the observation. The green persists. What if 60% probability became certainty? What would that mean for everything we thought we understood about our place in the cosmos? The PA trajectory data arrives next, and it is this information that transforms 3I Atlas from an oddity into a genuine mystery. Orbital mechanics specialists at NASA's Jet Propulsion Laboratory run the numbers. They trace the object's path backward through space, calculating where it must have originated. The results are published in the Minor Planet Center's database, available to anyone with an internet connection. 3I Atlas entered the solar system on a retrograde orbit, meaning it moves in the opposite direction to the planet's motion around the Sun. Its orbital inclination is approximately 175 degrees, nearly perpendicular to the plane of the solar system. This is not unusual for interstellar objects, which can arrive from any direction. What is unusual is the precision of its trajectory. The object will pass within 0.3 astronomical units of Mars on October 3, 2025. That is closer than Earth ever approaches Mars. It will reach perihelion, its closest approach to the Sun, on October 30, 2025, passing just 0.18 AU from our star. Then it will slingshot outward, passing near Jupiter's orbit in March 2026 before departing the solar system entirely. Statisticians calculate the odds. Given the random distribution of interstellar objects and the vast emptiness of space, what is the probability that a visitor would pass so close to two major planets and the Sun in a single trajectory? The numbers are uncomfortable. Roughly 1 in 500, like winning the lottery 3 times. In a row, one researcher notes privately, possible but suspicious. The object is not merely passing through our solar system, it is touring it, and the route it follows, whether by chance or design, offers unprecedented opportunities for observation. Opportunities that, if one were planning a reconnaissance mission, would be difficult to improve upon. Jason Wright, an astronomer at Penn State University, known for his work on technosignatures, weighs in publicly. He is skeptical of Loeb's 60% figure, calling it premature. The chemistry can be explained, Wright argues, by unusual formation conditions in another star system. The trajectory, while improbable, is not impossible. Coincidences happen. The universe is large, and statistically unlikely events occur with regularity when you sample enough space and time. But Wright also acknowledges the strangeness of the data. He does not dismiss the possibility of artificial origins outright. He simply argues for caution, for more observations, for resisting the temptation to jump to extraordinary conclusions before exhausting ordinary explanations. The debate is civil but pointed. Loeb and Wright represent two poles of interpretation, and between them, the astronomical community splits into camps. Some lean toward natural explanations, citing the need for parsimony and the long history of unusual comets eventually being understood through conventional science. Others find the accumulating anomalies difficult to ignore, each new data point adding weight to the hypothesis that 3I Atlas is not what it appears to be. And then on October 3rd, the object passes Mars. The Mars Reconnaissance Orbiter, equipped with the high-rise camera capable of resolving features as small as a few feet across, is tasked with imaging 3I Atlas as it approaches. Mars Express and ExoMars Trace Gas Orbiter join the effort. For a brief window, humanity has 3 spacecraft positioned to observe the visitor from relatively close range. The images they return will be analyzed for weeks, but the initial reports are tantalizing. HiRISE captures the object as a small, irregular shape, surrounded by a faint halo of gas. The resolution is not sufficient to reveal surface details, but the overall structure appears elongated. Perhaps cylindrical, perhaps not. The images are ambiguous, subject to interpretation. Some researchers see a natural nucleus with an asymmetric coma. Others see geometry, straight edges, symmetry that ice and rock should not possess. The photographs circulate, debates intensify, and 3I Atlas continues its journey, accelerating as it falls toward the sun, hurtling toward the perihelion that will occur on October 30th, hidden from Earth's view behind the blinding glare of our star. Carbon dioxide should not dominate a comet's outgassing. This is not opinion. It is observational fact accumulated over decades of studying comets throughout the solar system. From Halley to Hale-Bopp, from Wild 2 to 67P, Churyumov-Gerasimenko the pattern holds. Water ice forms the bulk of cometary material. Carbon dioxide exists, certainly, typically comprising between 2% and 20% of volatile gases, but never 95%. The JWST spectrum of 3I Atlas defies this pattern. On August 6th, when the telescope's near-infrared spectrograph locked onto the object, it captured not just the presence of carbon dioxide, but its overwhelming dominance. The spectral lines are unmistakable. The 426 micron absorption feature of CO2 ice is strong and clear. The water signatures at 3 microns are faint by comparison. The ratio is inverted by a factor of nearly 20 compared to typical comets. Stephanie Milam, the NASA astrochemist reviewing the data, later describes the finding as perplexing. She does not use the word impossible, though others will. She notes that carbon dioxide ice is less stable than water ice over long timescales. It sublimates more readily in the cold of interstellar space. For an object to arrive at our solar system with such a high CO2 content suggests either a very recent formation or some mechanism that preserved the volatile carbon dioxide while allowing water to escape. Neither scenario fits well with current understanding of comet evolution. Comets form in the outer regions of star systems, where temperatures are cold enough for volatiles to condense onto dust grains. In our own solar system, comets born in the Kuiper belt, or Oort cloud, carry the chemical signature of that formation. Environment. Water dominates because water ice is abundant and stable. Carbon dioxide, carbon monoxide, methane, and other volatiles exist as minor components. The chemistry reflects the temperature and pressure conditions at the time of formation. If 3I Atlas formed in another star system, the chemistry implies formation conditions radically different from our own. Perhaps it comes from a system where carbon dioxide ice was more abundant than water ice. Perhaps the protoplanetary disk from which it formed had an unusual chemical composition enriched in carbon and oxygen in different proportions than our Sun's nebula. Possible, but speculative. No such system has been observed directly, or perhaps the chemistry is not primordial at all. The data doesn't fit the models, and the models are built on thousands of comet observations spanning a century. Gemini South, the twin telescope to Gemini North, begins spectroscopic observations in late August. The instrument is equipped with high-resolution spectrographs capable of detecting trace molecules in cometary comas. The team focuses on searching for hydrogen cyanide, ammonia, methanol, and other organic compounds that typically accompany water outgassing in comets. What they find is absence. The expected suite of organic molecules is largely missing. HCN, usually prominent in comet spectra, appears at barely detectable levels. Methanol is absent. Ammonia is absent. It is like examining a recipe that calls for flour, eggs, and sugar, but finding only flour. The dish is incomplete, the chemistry is wrong. Dr. Wright's skepticism finds ground here. He suggests that the organic molecules may simply be frozen out, locked in ice that has not yet sublimated. As 3I Atlas approaches the Sun, heating should release these compounds. The coma should become more complex, more typical. We should see the chemistry shift toward normal cometary composition as solar radiation warms the nucleus and drives outgassing. Observations. In September, we'll test this prediction. But there is another anomaly in the chemistry, one that does not fit any comet model at all. On September 14th, the Very Large Telescope in Chile detects nickel in the coma of 3I Atlas. Not nickel ions, which might conceivably appear in trace amounts from dust grains, but metallic nickel vapor. The emission lines are clear and strong. Over the following weeks, the nickel signal intensifies by a factor of 25. Nickel outgassing from comets is rare, but not unknown. In 2021, astronomers detected both iron and nickel in the comae of several solar system comets, a discovery that surprised the community but was eventually attributed to the sublimation of metal-bearing minerals as the comets heated. Nickel and iron appeared together in roughly equal proportions as expected from the typical composition of meteoritic metal. 3I Atlas emits nickel but no iron, none detected. Finding nickel without iron is like finding smoke without fire. The two metals form together in stellar nucleosynthesis, mix together in planetary materials, and should sublimate together from cometary dust. They are chemically similar, bonded in the same mineral structures. There is no known natural process that would selectively release nickel while retaining iron. The VLT team, led by astronomers who declined to be named publicly, reports the finding in a brief circular submitted to the International Astronomical Union. They describe the observation. They provide measurements. They offer no explanation. The circular is technical, dry, and deeply unsettling to those who read it carefully. 25 times increase in nickel emission over 1 month. No corresponding iron. Chemistry that should not exist in nature. Some researchers speculate about exotic mineralogy. Perhaps 3I Atlas contains nickel sulfides or nickel carbonyls that could sublime independently of iron-bearing minerals. Perhaps the formation environment in another star system produced metal, ratios unlike anything in our solar system. Perhaps the observation is an error, an instrumental artifact, a misidentification of spectral lines. But the VLT is not a backyard telescope. Its instruments have detected metallic emissions in dozens of comets over the years. The team knows what nickel looks like. The measurement is solid. If natural explanations fail, what remains? The possibility that the nickel is not natural, that it is refined, purified, that the emission is not the result of sublimating minerals but something else entirely, something metallic and manufactured, outgassing not because of solar heating, but because of internal processes, machinery venting, systems cooling, technology operating. This is speculation, of course, controlled speculation framed with uncertainty. But it is speculation that the chemistry invites, even demands, once ordinary explanations are exhausted. Loeb, in an interview published on his blog in mid-September, seizes on the nickel anomaly. He argues that the selective emission of one metal without its typical companion is a signature that natural processes struggle to produce. He draws comparisons to industrial metallurgy, where nickel is refined and used in alloys for its resistance to corrosion and heat. He does not claim definitively that 3I Atlas is artificial, but he raises the question bluntly. What natural comet behaves this way? Wright responds, urging caution. Absence of evidence is not evidence of absence, he reminds. Readers, just because we have not observed iron in the spectrum does not mean it is not there. Perhaps the iron is bound in minerals that have not yet sublimated. Perhaps the observation window was limited. Perhaps further measurements will reveal iron and resolve the anomaly. But as September progresses and additional telescopes join the observation campaign, no iron appears. The nickel emission continues to strengthen. The ratio remains impossible. By the end of September, the chemical profile DAV3I Atlas has become a central mystery in its own right. The 95% carbon dioxide plume, the absence of organic molecules, and the nickel without iron emission combine to paint a picture that does not match any known comet. Each anomaly might be explainable individually through appeals to unusual formation conditions or selective observation windows. Together, they form a pattern that resists simple explanation. The object does not smell like a comet. It does not taste like a comet. It does not behave like a comet. And yet, if it is not a comet, what is it? The green glow persists in amateur photographs. Some researchers attribute it to diatomic carbon, as expected, but others note that the color is too saturated, too pure. They point out that diatomic carbon emissions are typically diffuse, spread across the entire coma. In photographs of 3I Atlas, the green appears concentrated near the nucleus, almost like a shell or layer surrounding the object. One amateur astronomer describes it as looking painted on. Another compares it to a neon sign. These are subjective impressions, not scientific measurements, but they contribute to the growing sense that something about this object is wrong, off, unnatural, and the object continues its approach, now less than 3 weeks from perihelion, less than 3 weeks from disappearing behind the Sun into a region of sky where Earth-based telescopes cannot follow. In 1974, physicist Ronald Bracewell published a paper proposing that advanced civilizations might explore the galaxy not with crude starships, but with autonomous probes. These probes would travel slowly between stars, perhaps over thousands or millions of years, arriving at planetary systems and conducting reconnaissance. They would be patient, intelligent, and subtle. Bracewell called them messenger probes, though the term Bracewell probes has since entered the lexicon of SETI research. The concept is elegant in its logic. Interstellar travel is difficult. Sending biological organisms across light years requires either faster-than-light travel, which physics forbids, or generation ships that must sustain life for centuries. Both are technologically daunting. Sending machines is simpler. Machines do not age. They do not require food or air. They can wait. They can repair themselves. They can observe and report back, or simply observe and record, fulfilling their mission across timescales that biology cannot endure. If such probes exist, how would we recognize them? This question has occupied SETI researchers for decades. The obvious signature would be intentional communication, a radio signal or laser pulse directed at Earth. But a probe might also choose to remain silent, observing without revealing itself. In that case, detection would require noticing something unusual about the object's behavior or composition, something that does not fit natural patterns. In 2018, following the discovery of Oumuamua, several researchers suggested that interstellar visitors might serve as scouts or precursors for more extensive exploration efforts. A civilization expanding slowly through the galaxy might send advanced probes to gather data before committing resources to contact or colonization. These precursor probes would need to be subtle, durable, and capable of autonomous operation over long durations. They would need to look, as much as possible, like natural objects. A comet is an excellent disguise. It moves through space propelled by gravitational forces, requiring no visible engines. It outgasses as it approaches a star, a natural process that could mask artificial emissions. It is small, difficult to resolve in detail, and expected to be irregular and chaotic in structure. If you wanted to send a probe through a star system without drawing attention, wrapping it in ice and rock would be a logical choice. This is the precursor hypothesis, and it is speculation. But it is speculation grounded in strategic thinking about how advanced civilizations might operate. 3I Atlas fits the profile uncomfortably well. It arrived from interstellar space on a trajectory that brings it close to multiple planets and the Sun. It exhibits chemical anomalies that resist natural explanation. It emits signals, metallic and otherwise, that do not match known cometary behavior. And it follows a path that offers optimal observation opportunities for anyone or anything aboard. Consider the trajectory more carefully. The object approaches Mars first, passing within 0.3 AU on October 3rd. Mars is a target of intense scientific interest, a planet where humanity has placed multiple orbiters and rovers, a world we are actively studying as a potential site for future exploration and habitation. Any reconnaissance mission surveying the solar system would want to examine Mars closely. Then 3I Atlas swings inward, diving toward perihelion on October 30th. This brings it near the Sun, the energy source that powers the entire system. Solar observation, solar gravity measurements, magnetic field mapping, all would be valuable data for understanding a star system's dynamics. Finally, the object passes near Jupiter in March 2026. Jupiter dominates the outer solar system, a gas giant whose gravity shapes the orbits of everything around it. Its moons are complex worlds, some with subsurface oceans potentially capable of supporting life. Jupiter is not a planet you would skip if you were surveying this system. 3 major targets, 1 trajectory. Statistical odds, 1 in 500 that this path is random. Like a chess move we didn't see coming. The strategy is clear once you notice it, but the intent remains ambiguous. Wright, when pressed on the precursor hypothesis during a podcast interview in late September, acknowledges its coherence, but emphasizes the lack of direct evidence. "You can construct a scenario where everything fits," he says. "That doesn't make it true. You need positive evidence of technology, not just absence of good natural explanations. You need engineering signatures. You need something that nature cannot do, full stop. And what would that look like? Shape is one possibility. If 3I Atlas is artificial, its structure should exhibit geometric regularity. Straight edges, right angles, cylindrical or spherical symmetry. The high-rise images from Mars Reconnaissance Orbiter hint at elongation, but the resolution is insufficient for definitive conclusions. Better images might come from closer flybys, but there are no missions positioned to intercept the object. Signals are another possibility. Radio emissions, laser pulses, infrared radiation inconsistent with thermal glow. Searches have been conducted. The SETI Institute pointed the Allen Telescope Array at 3I Atlas in early September, listening across a wide band of radio frequencies for any indication of artificial transmission. They found nothing. Silence across the spectrum. But silence does not mean absence. A probe designed for reconnaissance would likely avoid active transmission, which would reveal its presence. It would passively collect data, perhaps storing it for later relay or simply recording observations for its own purposes. We would not expect to hear it unless it wanted to be heard. Acceleration is a third possibility. Oumuamua famously exhibited non-gravitational acceleration, a tiny but measurable deviation from the path gravity alone would produce. Some researchers attributed this to cometary outgassing, the rocket effect of sublimating ice pushing the object slightly off course. Loeb argued it was consistent with a light sail, a thin, reflective surface pushed by solar radiation. 3I Atlas shows no such acceleration. Its orbit follows gravitational predictions precisely. This might seem to argue against artificial origins, but it could also indicate superior design. If the object is a probe, its builders might have ensured it moves purely under gravity to avoid detection. Cometary outgassing is chaotic and difficult to hide. Pure ballistic flight is simple and silent. Every answer opens a bigger question. If 3I Atlas is a probe, it is a masterfully engineered one, mimicking nature so closely that distinguishing it from a comet requires scrutinizing anomalies in chemistry and statistics. If it is not a probe, then nature has produced something unprecedented, an interstellar comet with properties that defy decades of accumulated knowledge about how these objects should behave. By late September, the debate has reached beyond academic journals and conference rooms. Media outlets pick up the story. Headlines range from cautious to sensational. Harvard scientist says 60% chance interstellar object is alien probe, appears on space news websites. Astronomers baffled by bizarre chemistry of interstellar visitor runs in science magazines. The story spreads, capturing public attention in a way that most astronomical discoveries do not. The attention brings scrutiny. Other researchers weigh in, some defending the natural comet interpretation, others acknowledging the strangeness without committing to conclusions. The Minor Planet Center receives dozens of requests for updated orbital data. Observatories around the world add 3I Atlas to their schedules. The object has become one of the most intensely studied celestial bodies in recent memory. And it continues its journey. Now just 2 weeks from perihelion, 2 weeks from passing behind the Sun, where ground-based telescopes will lose sight of it for months. Whatever 3I Atlas is, whatever secrets it carries, it is about to vanish from view. The timing is unfortunate, or perhaps it is not. Mass is one of the most fundamental properties of any celestial object. It determines gravitational influence, orbital dynamics, and physical structure. For comets, mass can be estimated through several methods, measuring how the object gravitationally perturbs nearby bodies, observing the volume and density based on size estimates, or calculating from the rate of outgassing and assumptions about composition. For 3I Atlas, all three methods have been attempted. The results are troubling. Photometric observations, tracking how sunlight reflects off the object, suggest a nucleus roughly 1.5 kilometers in diameter. This is large for a comet, but not extraordinary. Hale-Bopp, one of the great comets visible to the naked eye, had a nucleus estimated at 60 kilometers. Halley's comet is about 15 kilometers. 3I Atlas at 1.5 kilometers is modest, but the mass does not match. On September 20th, researchers at the Jet Propulsion Laboratory publish updated orbital calculations. They have been tracking 3I Atlas's trajectory for months, integrating gravitational data from the Sun, planets, and other solar system bodies. The precision of modern astrometry allows them to detect tiny perturbations in the object's path caused by gravitational interactions. When they factor in the observed trajectory deviations during the Mars flyby on October 3rd, the implied mass is staggering. 33 billion metric tons. That is the mass required to produce the gravitational signature observed as the object passed Mars. 33 billion tons for an object 1.5 kilometers across implies a density far higher than any comet ever measured. Water ice has a density of roughly 920 kilograms per cubic meter. Rock is denser, around 3,000 kilojoules m3. Even solid iron is only 7,800 kilojoules m3. To pack 33 billion tons into a 1.5 kilometer sphere would require an average density exceeding that of lead. Comets are not made of lead. They are fluffy, porous aggregates of ice and dust. Typical comet densities range from 400 to 600 kilo m3, less dense than water because of the empty space between grains. A solid ice ball would be denser, but still far lighter than what the orbital data suggests. The numbers do not reconcile. Either the size estimate is wrong, and 3I Atlas is much larger than photometry indicates, or the density is impossibly high. Some researchers favor the first option. Perhaps the object is dark, reflecting very little light, making it appear smaller in telescopes than it actually is. A larger nucleus would lower the implied density to more reasonable values. But spectroscopic observations contradict this. The brightness variations as 3I Atlas rotates suggest a relatively small, compact object, not a large one. The light curve, the graph of brightness over time, shows modulations consistent with a body roughly 1 to 2 kilometers in size, tumbling through space. A 10-kilometer object would produce a different light curve, more gradual fluctuations and less perfectly spherical, so the size estimate appears solid, which leaves the density problem unresolved. Tom Statler, a planetary scientist at NASA headquarters, suggests cautiously that the gravitational data may be contaminated by outgassing forces. Even though no non-gravitational acceleration is directly observed, the rocket effect from sublimating gases might subtly alter the orbit in ways that mimic additional mass. "We're dealing with very small perturbations," Statler notes in an email interview. "It's possible we're misinterpreting the signal." But the Mars flyby provides an opportunity to cross-check. The three spacecraft orbiting Mars, MRO, Mars Express, and ExoMars TGO, all tracked 3I Atlas as it passed. Their orbital positions shifted ever so slightly due to the visitor's gravitational pull. Independent measurements from all three spacecraft confirm the mass estimate, 33 billion tons. Like a locked safe drifting through space, we don't know what's inside, but the weight is wrong. If the mass is real, if the density is truly as high as the data suggests, then 3I Atlas cannot be a normal comet. It would need a substantial core of heavy material, metal perhaps, or something even denser. The icy coma and carbon dioxide outgassing would be a surface layer, a shell, covering a massive interior. This is not impossible in principle. Some asteroids have metallic cores, remnants of differentiated planetesimals that formed early in solar system history and later shattered, exposing their iron-nickel interiors. M-type asteroids, as they are classified, are thought to be fragments of such cores. They are dense, metallic, and valuable for future mining efforts if humanity ever develops the technology to exploit them. But 3I Atlas is not from our solar system. It arrived from interstellar space. For it to possess a metallic core, it would need to have formed in a planetary system where differentiation occurred, where rocky bodies melted and separated into layers of metal and silicate. Then that body would need to be shattered, ejected from its system, and sent on an interstellar journey that brought it here. Possible, but adding complications to an already strained narrative. Wright suggests an alternative during an online debate hosted by a planetary science forum. Perhaps 3I Atlas is a contact binary, two objects loosely bound together, tumbling in mutual orbit. If one component is denser than the other, the combined mass could be higher than a single icy nucleus would suggest. The photometry might be dominated by one component, making the system appear smaller than it is. This is plausible. Contact binaries are known in the solar system. Comet 67P, visited by the Rosetta spacecraft, consists of two lobes connected by a narrow neck, likely the result of a low-speed collision. If 3I Atlas is similar, the mass anomaly might dissolve, but the light curve does not strongly support a binary structure. The brightness variations are too smooth, lacking the sharp dips that would occur if two distinct bodies were eclipsing each other from our perspective. The rotation appears to be that of a single, irregularly shaped object, not two bodies in mutual orbit. The data doesn't fit the models, and every attempt to reconcile the mass with the size produces new problems. By the end of September, the mass anomaly has joined the chemistry anomalies in the growing dossier of things that make 3I Atlas strange. The object is too dense, its composition is wrong, its trajectory is suspicious, and it is about to disappear. On October 30th, 3I Atlas will reach perihelion, passing just 0.18 AU from the Sun. At that distance, solar glare will overwhelm any attempt to observe it from Earth. Ground-based telescopes will lose sight of it. Space-based observatories like Hubble, which must avoid pointing too close to the Sun to protect their instruments, will also be unable to track it. There is one telescope that might manage: the Solar and Heliospheric Observatory, SOHO, which constantly monitors the Sun and has detected thousands of comets that pass through its field of view. But SOHO's resolution is limited. It can capture images, but not spectra. It can confirm the object's presence, but not analyze its composition or structure in detail. For roughly 2 months from late October through early December, 3I Atlas will be invisible to most of humanity's instruments. It will pass perihelion alone, hidden behind the Sun, whatever processes occur at that closest approach concealed from view. When it reappears in December, will it look the same? Will the chemistry remain anomalous? Will the mass still defy explanation? Or will the intense solar heating alter the object in ways that clarify its nature, revealing either natural processes at work or something else entirely? If amateurs see structure and professionals dismiss it, who should we trust? The question is rhetorical, of course. Science requires reproducibility, peer review, and evidence that withstands scrutiny. Amateur observations are valuable, but they must be confirmed by professional instruments before conclusions are drawn. And yet, the history of astronomy is filled with examples of amateurs making discoveries that professionals initially dismissed. Comets, novae, supernovae. Countless transient phenomena were first spotted by backyard observers who happened to be looking at the right patch of sky at the right time. The green glow photographed by amateurs persists in the record. The professional explanations, diatomic carbon ionization effects, are reasonable but incomplete. The color is too pure, too concentrated. Something about the emission does not quite match the standard model, and the mass problem has no amateur equivalent. This is data from NASA, from ESA, from orbital mechanics, calculated by professionals using the best instruments available. 33 billion tons. A number that should not exist for an object of this size and apparent composition. As October begins and the clock counts down toward perihelion, the astronomical community waits. Observations continue. Spectra are recorded. Photometry tracks the object's rotation and brightness. Every piece of data is catalogued, analyzed, and debated. But the consensus remains elusive. For every natural explanation proposed, an anomaly persists. For every anomaly highlighted, a counter-argument is raised. The object sits in a strange liminal space between comet and something else, its true nature obscured by both the limits of our instruments and the distance that separates us. And then on October 3rd, as 3I Atlas passes Mars, one final observation emerges that will shift the debate once more. In the history of astronomy, timing is everything. A supernova, discovered too late, cannot be studied in its initial explosion. A near-Earth asteroid spotted only after it passes offers no opportunity for detailed observation. The universe operates on its own schedule, indifferent to human readiness. For 3I Atlas, October 30th is not just perihelion, it is occultation. The date when the object passes behind the Sun from Earth's perspective, vanishing from our instruments for 2 months. Astronomers have known this since the orbit was first calculated in June. They have had time to prepare, to schedule observations, to gather as much data as possible before the visitor disappears. But knowing something will happen and understanding why it happens that way are different things. The orbit of 3I Atlas is not unique in passing behind the Sun. Many comets do this. It is a consequence of orbital mechanics, of the geometry of elliptical paths around a gravitational center. What makes this occultation notable is its duration and its timing relative to the object's discovery. The object was detected in late May 2025, roughly 5 months before perihelion. This is not an unusually short warning time for interstellar visitors. Oumuamua was discovered after its closest approach to the Sun, already on its way out of the system. Borisov was found earlier in its trajectory, allowing months of observation. 5 months is reasonable, adequate. But when the full orbit is calculated, a pattern emerges that is difficult to dismiss as coincidence. 3I Atlas entered the inner solar system from the direction of the constellation Draco, approaching from above the plane of the ecliptic at a steep angle. Its arrival from this direction meant it remained relatively faint and distant until June, when it crossed closer to Earth's orbital path and brightened enough for Atlas to detect it. Before June, the object was too faint, lost in the vastness of space. After October 30th, it will pass behind the Sun, invisible until December, when it emerges on the other side. Then it will rapidly recede, dimming as it moves outward toward Jupiter and eventually beyond, fading below detection limits by mid-2026. The observation window is narrow: 5 months of approach, 2 months of occultation, then a few months of departure before it becomes too faint to study. If you wanted to limit how long a civilization could examine you, this trajectory would be effective. Controlled speculation, yes, but speculation that the data invites. On October 15th, 2 weeks before, perihelion, a team of researchers publishes a brief paper on the preprint server Archive. The paper is titled Geometric and Temporal Constraints on Observation of Interstellar Object 3I Atlas. It is dry, technical, and careful not to make extraordinary claims, but the conclusion is clear. The trajectory of 3I Atlas limits observation opportunities in ways that are statistically unusual. The authors calculate visibility windows for Earth-based telescopes, space-based observatories, and planetary missions. They factor in solar glare, orbital geometry, and instrumental limits. The result is a graph showing when the object is observable and when it is not. The observable windows are small. The occultation period is long. The overall pattern minimizes the time during which detailed study is possible. 1 in 500 chance, the statisticians said earlier about the close approaches to Mars and Jupiter. Now the timing adds another layer, not just where the object goes, but when it can be seen. Like a chess move we didn't see coming. If you were planning a reconnaissance mission and wanted to avoid prolonged scrutiny, you would time your closest approach to coincide with periods when observation is difficult. You would pass behind the Sun. You would emerge when already receding, too far for detailed imaging. You would leave before anyone could organize a dedicated intercept mission. Jason Wright, in a blog post responding to the Arxiv paper, reiterates his caution. Unusual. Timing is not evidence of intent, he writes. We observe what we can when we can. Selection bias is real. We notice the objects that happen to be bright enough and close enough when we're looking. If 3i Atlas had arrived a year earlier or later, we might never have seen it at all. The fact that we did see it and that the observation window is narrow tells us more about our limitations than about the object's purpose. Valid points. Science demands skepticism, but the counter-question persists. At what point does accumulation of improbable features become evidence rather than coincidence? No single anomaly proves anything. The chemistry is strange, but potentially explainable. The mass is high, but might be reconciled with better models. The trajectory is improbable, but not impossible. The timing is unfortunate, but could be bad luck. Each piece alone is insufficient. Together, they form a pattern. And now, as October 30th approaches, astronomers face a dilemma. The object is about to vanish. Whatever data can be gathered must be gathered in the next 2 weeks. After that, 3i Atlas will be alone, hidden behind the most powerful light source in the solar system, unreachable and unobservable. The James Webb Space Telescope allocates additional observation time. Hubble joins in, pushing the limits of how close to the Sun it can safely point. Ground-based observatories coordinate a global campaign. Telescopes in Chile, Hawaii, Australia, and South Africa, all training on the same target, collecting spectra, photometry, and astrometric data around the clock. The urgency is palpable in the astronomical community. Not panic, but pressure. The sense that time is running out. On October 20th, the Parker Solar Probe, NASA's mission to study the Sun, approaches one of its closest perihelion passes. Parker is designed to survive extreme heat and radiation, diving to within a few million kilometers of the solar surface. Its trajectory brings it relatively near the predicted path of 3i Atlas, though not close enough for a direct encounter. Mission planners realize that Parker's instruments might glimpse the interstellar visitor as both objects swing around the Sun. Parker's Whisper camera, designed to image the solar corona, could potentially capture 3i Atlas if it passes through the field of view. The spacecraft is not designed for this purpose. Its instruments are optimized for solar observation, not comet tracking. But the opportunity is too valuable to ignore. Commands are uploaded. Parker's cameras are programmed to take additional images during the perihelion pass, scanning the region where 3i Atlas is expected to appear. The data will not be transmitted immediately. Parker's orbit carries it far from Earth, and communication windows are limited. But when the images do arrive in early November, they will offer a unique perspective, a view from inside the observation gap, from the region where ground-based telescopes cannot see. If 3i Atlas does anything unusual during perihelion, anything that deviates from expected cometary behavior, Parker might witness it. The final ground-based observations occur on October 28th. By this date, the object is less than 48 hours from perihelion and already difficult to observe through the solar glare. Telescopes must point dangerously close to the Sun, risking instrument damage from scattered light. Observations are brief, hurried, incomplete. The last spectrum, captured by the Very Large Telescope, shows the nickel emission still strong, still unaccompanied by iron. The carbon dioxide plume persists, still dominating over water vapor. The green glow remains visible in the final amateur photographs uploaded to online forums, and the object's brightness, which should be increasing rapidly as it approaches the Sun, shows a strange plateau, as if the outgassing has stabilized rather than accelerated. Comets typically brighten dramatically as they near perihelion. Solar heating drives intense sublimation, releasing vast amounts of gas and dust that scatter sunlight and make the coma and tail glow brightly. But 3i Atlas, in its final days of visibility, does not follow this pattern. Its brightness increases, yes, but more slowly than models predict, as if something is regulating the outgassing, as if the process is controlled rather than chaotic. On October 30th at 14:37 Universal Time, 3i Atlas reaches perihelion. The exact moment when it is closest to the Sun, just 0.18 astronomical units away, roughly 27 million kilometers. At this distance, the solar radiation is intense, enough to vaporize ice rapidly, to drive complex chemistry, to alter the object's surface and structure. No telescope on Earth can observe it. The Sun's glare is absolute. SOHO's cameras might capture a faint smudge as the object transits through the field of view, but nothing detailed. For the next 2 months, 3I Atlas is alone with the Sun, and humanity waits. Every answer opens a bigger question. If this is a natural comet, why does it behave so strangely at every stage? If this is something else, why reveal itself through subtle anomalies rather than clear signals? What happens during occultation that we cannot see? And when the object reappears in December, what will it look like? The occultation is not just a gap in data, it is a test of patience, of models, of theories. If 3I Atlas emerges in December looking the same, chemistry unchanged, mass still anomalous, then the mystery persists. If it emerges transformed, more comet-like, then perhaps the heating at perihelion resolved the anomalies, revealing mundane processes beneath the initial strangeness. Or if it does not emerge at all. This is the darker speculation, whispered in online forums and late-night conversations among researchers. What if the object does not reappear? What if it changes course during occultation, when no one is watching, and departs on a different trajectory? Orbital mechanics says this is nearly impossible without thrust, without engines. But if 3I Atlas is not what it appears, if it possesses propulsion beyond cometary outgassing, then the occultation offers a perfect opportunity to maneuver unseen. The data doesn't fit the models, and now the data has disappeared entirely, hidden behind 1.4 million kilometers of glowing plasma that we call the Sun. October ends. November begins. Astronomers analyze the data collected over the past 5 months, writing papers, comparing notes, debating interpretations. The JWST spectra are scrutinized line by line. The VLT nickel measurements are checked and rechecked. The orbital calculations are refined to the limits of precision. And slowly, a picture emerges. Not a complete picture, but fragments of one. An object that arrived from interstellar space carrying chemistry that should not exist. An object whose mass exceeds what its size should allow. An object whose trajectory brings it close to planetary targets of interest. An object that times its closest approach to coincide with maximum observation difficulty. Individually, each piece is anomalous but potentially explainable. Collectively, they suggest something that astronomy has never confirmed, but has long speculated about. A visitor that is not random, not natural, but designed. Avi Loeb's 60% probability does not shift. He maintains his assessment through October, arguing that the accumulation of anomalies strengthens the case for artificial origins. He does not claim certainty. He does not assert that 3I Atlas is definitely a probe, but he argues that the possibility must be taken seriously, that the data warrants investigation beyond what standard comet studies provide. Jason Wright's skepticism also holds. He continues to point out that extraordinary claims require extraordinary evidence, and that anomalies, however strange, are not proof. He calls for more data, more observations, more time to study the object before conclusions are drawn. Both are right in their own ways. Both are reacting to the same data from different philosophical starting points, and both will have to wait until December to see what happens next. Because in December, 3I Atlas is scheduled to reappear. The orbital calculations are clear. The object should emerge from behind the Sun on December 3rd, visible again to Earth's telescopes, continuing its journey outward toward Jupiter. If the orbit is accurate, if nothing has changed, if the object remains on its predicted path, then observation can resume. But if the occultation has altered something, if the intense solar heating at perihelion has triggered changes we cannot predict, then what emerges in December might not be what disappeared in October. The wait is agonizing for those following the story. 2 months of silence, 2 months of speculation without data, 2 months during which the object, whatever it is, passes closer to the Sun than Mercury ever does, experiencing conditions that only the most robust comets survive intact. Will it survive? Should we want it to? Numbers do not lie, but they can mislead. Statistics offers probabilities, not certainties. A 1 in 500 chance is unlikely, but not impossible. Flip a coin 500 times and you might see 50 heads in a row. Improbable, yes. Evidence of a weighted coin, perhaps, but not proof. The trajectory of 3I Atlas is that coin flip, and astronomers are divided on what it means. The orbital analysis published by the Jet Propulsion Laboratory in late September provides the raw numbers. The object's path through the solar system brings it within 0.3 AU of Mars, 0.18 AU of the Sun, and will pass within 1.2 AU of Jupiter in March 2026. These are close approaches by astronomical standards, particularly for an object arriving from interstellar space with no prior connection to our system's dynamics. To calculate the probability of such a trajectory, researchers model the distribution of random interstellar visitors. They assume a steady influx of objects entering the solar system from all directions, with velocities and angles distributed according to observed patterns. They then calculate what fraction of these hypothetical visitors would pass as close to as many major bodies as 3I Atlas does. The result? Approximately 1 in 500. This number has been repeated in media coverage, in scientific discussions, in online debates. It has become shorthand for the strangeness of the trajectory. But what does it actually mean? In probability theory, low probability events occur regularly when the sample size is large enough. If interstellar objects pass through the solar system frequently, then 1 in 500 trajectories will appear occasionally. The question becomes, how many interstellar visitors have there been? We know of 3 confirmed interstellar objects, Oumuamua, Borisov, and 3I Atlas, but these are only the detected ones. Detection requires that an object be bright, enough and close enough when someone happens to be looking. Most interstellar visitors likely pass through unnoticed, too faint or too far away to trigger alerts in survey systems. Statistical models estimate that interstellar objects may transit the inner solar system once or twice per year. If true, then hundreds have passed through during the history of modern astronomy. 3 detected out of hundreds means our observation efficiency is low, perhaps a few percent. If hundreds have passed undetected, then eventually one should have a trajectory like 3I Atlas. The 1 in 500 chance becomes not a sign of design, but an inevitability over time. We were bound to see something unusual eventually, and this is it. This is the skeptical interpretation, and it is statistically sound. But there is a counter-argument, one that does not reject the statistical reasoning, but questions the assumptions underlying it. The assumption of random trajectories depends on interstellar objects being distributed evenly across space, with no preferred directions or velocities. This is reasonable for natural objects ejected from other star systems by gravitational interactions. They would leave their home systems in random directions, traveling through the galaxy without guidance, eventually encountering other stars by chance. But if even a small fraction of interstellar visitors are not natural, if some are directed, then the statistical model breaks down. A probe sent deliberately to survey our solar system would not arrive on a random trajectory. It would be aimed. Its path would be optimized to pass near objects of interest, planets, the Sun, gas giants. Such a trajectory would look statistically unlikely, precisely because it is unlikely for random objects, but likely for designed ones. Distinguishing between unlikely but natural and unlikely because designed requires more than trajectory analysis alone. It requires chemistry, mass measurements, and detailed observation of the object's structure and behavior. And it requires finding signatures that nature cannot produce. The nickel emission might be such a signature, the mass anomaly might be another, but each has potential natural explanations that, while strained, are not impossible. The statistical trajectory adds context. It raises the prior probability that something unusual is happening, making the chemical and mass anomalies more significant than they would be for a randomly wandering comet. Think of it as Bayesian reasoning. We start with a prior belief about the likelihood of artificial objects passing through the solar system. For most astronomers, this prior is extremely low. Interstellar travel is hard. The galaxy is vast. The chance that an alien probe happens to visit our specific system during the brief century when we have telescopes to detect it seems vanishingly small, but each piece of evidence updates that prior. An unusual trajectory shifts the probability slightly. Upward. Strange chemistry shifts it further. A mass anomaly adds more weight. At some point, if enough independent anomalies accumulate, the posterior probability that the object is artificial might exceed the probability that it is natural, even if no single piece of evidence is definitive. This is where Loeb's 60% figure comes from. Not from any single measurement, but from integrating multiple anomalies and assessing which hypothesis better explains the totality of observations. It is subjective, yes. Another researcher might weigh the evidence differently and arrive at 40% or 10% or 90%, but the approach is valid. Use all available information to estimate likelihoods. Jason Wright, in his published critiques, does not dispute the Bayesian framework. He disputes the weighting of evidence. He argues that the natural explanations, while imperfect, are still more plausible than invoking artificial origins, which requires accepting the extraordinary claim that alien technology exists and has reached our solar system. Extraordinary claims require extraordinary evidence, and for Wright, the current data does not meet that threshold. The debate is methodological. How much weight should we assign to improbable trajectories, strange chemistry, and anomalous mass? How much should we penalize the hypothesis that aliens are visiting us, given the lack of prior confirmed contact? There is no objective answer. Science proceeds by argument, by testing hypotheses against data, by peer review and reproducibility. The truth emerges over time as more evidence accumulates, but for 3I Atlas, time is limited. The occultation has closed the observation window. The object is hidden, and when it reappears, the opportunity for detailed study will be brief before it fades into the outer solar system and vanishes from our instruments permanently. In November, while the object remains occulted, researchers focus on analyzing the existing data with greater rigor. One team examines the rotation period, deriving a more precise estimate of approximately 16 hours based on the light curve fluctuations observed in September. This rotation rate is consistent with a single, irregularly shaped body tumbling through space. It is not consistent with a rapidly spinning object or a system in tidal lock. If the object is artificial, the rotation suggests it is not actively stabilized. Spacecraft typically control their orientation using gyroscopes or thrusters, maintaining specific attitudes for communication or solar panel alignment. 3I Atlas tumbles chaotically, as a natural object would. This is evidence against artificial origins or evidence of an inactive or derelict probe. Another team revisits the photometry, searching for periodic variations that might indicate surface features or geometric structure. They find nothing definitive. The brightness changes are smooth, lacking sharp edges or patterns that would suggest discrete panels or reflective surfaces. If there is geometry hidden in the object, it is masked by the coma or too subtle to detect at current resolution. A third team analyzes the green emission captured in amateur photographs. They model the expected emission from diatomic carbon at various concentrations and compare it to the observed color. The match is reasonable but not perfect. The observed green is slightly more saturated than the model predicts, suggesting either higher concentrations of C2 than typical for comets or an additional emission source. Could there be an artificial light source? A glow from internal systems leaking through the coma? The speculation is wild, but it fits the data as well as the natural explanation. Without higher resolution spectra, distinguishing between the two is impossible. The data doesn't fit the models, but the models are incomplete based on observations of solar system comets that may not represent the full diversity of interstellar visitors. One researcher, speaking anonymously to avoid professional backlash, summarizes the situation bluntly. We're trying to diagnose a patient we've never seen before using medical knowledge from a different species. Every test comes back abnormal, but we don't know if that's because the patient is sick or because our norms don't apply. The analogy is apt. 3I Atlas is a sample size of 1. We have no baseline for what interstellar comets should look like. Borisov, the previous interstellar comet, appeared relatively normal, matching expectations for a comet from another star system. But Oumuamua was bizarre, tumbling, elongated, accelerating without visible outgassing. And now 3I Atlas is strange in its own ways. Perhaps interstellar comets are simply weirder than their solar system cousins. Perhaps the conditions in other star systems produce ices with different compositions, structures with different densities, behaviors that do not match our experience. If so, every interstellar visitor will seem anomalous until we have observed enough of them to understand the new normal. Or perhaps most interstellar visitors are normal, and the strange ones are strange for a reason. The statistical shadow deepens. The 1 in 500 trajectory is not proof, but it is uncomfortable. Combined with the chemistry, the mass, the timing, the occultation, the pattern suggests something beyond random chance, not conclusively, not definitively, but enough to warrant serious consideration. In mid-November, a group of researchers submits a proposal to NASA for a rapid response mission to intercept 3I Atlas during its outbound journey. The proposal outlines a small spacecraft launched quickly using existing rocket systems that could rendezvous with the object in late 2026 or early 2027 before it leaves the solar system. The mission would carry cameras, spectrometers, and instruments capable of close-range analysis. It would answer, once and for all, whether 3I Atlas is a comet or something else. The proposal is ambitious and expensive. Rapid missions are difficult to plan and execute. Launch windows are narrow. The trajectory matching required to catch an interstellar object is complex. Funding such a mission on short notice without years of planning and review is nearly unprecedented. NASA responds cautiously. The proposal is under consideration. Preliminary feasibility studies are commissioned, but no commitment is made. The agency, like the broader scientific community, is waiting for December, waiting to see if 3I Atlas reappears as predicted, and if it does, what it looks like. If the object emerges with chemistry and behavior more consistent with a normal comet, the urgency for a mission diminishes. If it remains anomalous, or becomes more anomalous, the case for interception strengthens. But either way, the decision will not be made until the observation gap closes. November passes slowly. The news cycle moves on to other stories. Media attention fades. But within the astronomical community, the waiting continues. Telescopes are scheduled, data analysis proceeds, and speculation, controlled but persistent, fills the silence. What is happening behind the sun? Is the intense solar heating altering the object, stripping away the ice to reveal what lies beneath? Is the chemistry changing, the carbon dioxide sublimating entirely, leaving only rock or metal? Is the trajectory shifting, subtle course corrections executed while no one watches? Or is it simply a comet enduring the perihelion passage as countless comets have before, unchanged and unchanging, waiting to be seen again? The answers will come in December, or they will not come at all. December 3rd, 2025. The date circled on calendars across dozens of observatories. The predicted reappearance of 3I Atlas, emerging from behind the sun after 2 months of occultation. In Chile, the Very Large Telescope points toward the expected coordinates. In Hawaii, the twin Keck telescopes stand ready. Gemini South, Pan-STARRS, and a network of smaller observatories scattered across the southern hemisphere all focus on the same patch of sky. The prediction is based on orbital mechanics, on the calculated trajectory that should carry the object in a smooth arc around the sun. If the orbit is accurate, 3I Atlas should appear in the pre-dawn sky just before sunrise, moving slowly against the background stars. It should be faint, still relatively close to the sun and difficult to separate from solar glare, but detectable with large telescopes and careful observations. The first confirmation comes at 03:17 Universal Time from the VLT. A faint point of light in the expected location, moving at the expected rate. The object has reappeared. It is still there, still on course. Within hours, other observatories confirm. Gemini South captures an image. Pan-STARRS logs the detection. Keck obtains a preliminary spectrum. The astronomical community exhales. Whatever happened during occultation, the object survived perihelion and remains on its predicted trajectory. But has it changed? The first spectra are noisy, taken at the limits of what the instruments can resolve, given the object's proximity to the Sun. But even in these early observations, patterns emerge. The carbon dioxide emission is weaker than before. Not absent, but significantly reduced. Water vapor has increased, now comprising a larger fraction of the coma than it did in September. The ratio is shifting towards something more normal, more comet-like. This is expected. Comets typically lose their more volatile ices first. Carbon dioxide sublimates at lower temperatures than water ice. As the object approached perihelion and heated, CO2 would have vaporized preferentially, depleting the surface layers. Now moving outward from the Sun, the remaining outgassing would be dominated by water, the more stable ice that requires higher temperatures to sublimate. The chemistry is normalizing. The anomaly is fading. But the nickel emission persists. Observations on December 5th by the VLT confirm strong nickel lines in the spectrum, weaker than in September, but still present, and still no iron. The selective emission that should not exist continues. The mass measurements are more difficult to update. With the object now outbound and no close planetary encounters scheduled until March, there are few gravitational interactions to analyze. The mass estimate of 33 billion tons remains on the record, neither confirmed nor refuted by new data. And the object's brightness is fading faster than models predict. Photometry conducted in the first week of December shows 3I Atlas dimming rapidly as it recedes from the Sun. This is normal. All comets fade as they move away from solar heating. But the rate of dimming exceeds what the initial outgassing measurements suggested. It is as if the object's reflectivity has decreased, or the active area producing the coma has shrunk more than expected. Some researchers interpret this as the coma dissipating, the remaining ice sublimating away, to reveal a darker, less reflective nucleus beneath. Others suggest the object might have fragmented during perihelion, breaking apart under thermal stress, with the pieces now separating and fading individually. Fragmentation is common for comets. Many do not survive close perihelion passages. The tidal forces and thermal stresses can tear loosely bound nuclei apart, scattering fragments that quickly dim and vanish. If 3I Atlas fragmented, it would explain the rapid brightness decline, and might also explain some of the earlier anomalies. Perhaps the high mass was due to a denser central fragment surrounded by looser material that has now dispersed. But fragmentation should produce multiple distinct points of light, separating over time as the pieces drift apart. Observations in mid-December show no clear evidence of multiple components. The object appears as a single fading source, its coma less extensive than before but still coherent. The data doesn't fit the models. Even as some anomalies resolve, others persist or deepen. By December 20th, the object has faded to near the limits of detection for all but the largest telescopes. Follow-up observations are still possible, but increasingly difficult. The window for detailed spectroscopy has closed. Photometry continues, tracking the object's position and brightness, but the chemistry and composition are now locked in the record, unchangeable, without new instruments or closer approaches. And the next close approach will be Jupiter, in March 2026, still 3 months away. The astronomical community takes stock. What have we learned from the reappearance? What questions have been answered, and what questions remain? The chemistry has shifted toward normal. The overwhelming dominance of carbon dioxide has diminished, replaced by a more typical water-dominated coma. This suggests that whatever unusual ice composition existed on the surface has sublimated away, leaving deeper layers that match expectations. The anomaly was real but temporary, a surface effect rather than a bulk property. Or perhaps the surface layer was the anomaly because it was designed to be. A coating of carbon dioxide ice could serve as thermal protection, ablating during close solar passage to shield internal systems. Once the coating is gone, the underlying material becomes visible, and it might be water ice, or it might be something else camouflaged, to look like water ice in spectra. Speculation, yes, but framed with caution, acknowledging uncertainty. The nickel emission persists, and this remains unexplained. No natural process has been proposed that satisfactorily accounts for nickel without iron, especially at the levels observed. The anomaly has not resolved. It has simply faded along with the overall brightness of the object, suggesting the source is diminishing but still active. The mass question hangs unanswered. Without new gravitational measurements, the 33 billion ton estimate cannot be refined or refuted. It stands as a data point that does not fit any simple model, neither fully explained nor dismissed, and the trajectory continues unchanged. The object is on course for Jupiter, following the path predicted months ago. If it maneuvers, if it alters its orbit while hidden behind the Sun, the changes are too subtle to detect. The trajectory remains statistically improbable, but gravitationally consistent. Avi Loeb, in a blog post published on December 22nd, reaffirms his 60% assessment. He argues that the persistence of the nickel anomaly and the rapid brightness decline are consistent with artificial origins. He suggests the object might have jettisoned material during perihelion, expelling a protective coating or shedding components no longer needed, accounting for the brightness change. He does not claim certainty, but he maintains that the evidence taken together favors the hypothesis that 3I Atlas is not a natural comet. Jason Wright, responding in a follow-up post, acknowledges the nickel anomaly as troubling, but reiterates that extraordinary claims require extraordinary proof. He argues that the chemistry normalization suggests natural processes are at work, and that the mass anomaly might be an artifact of observational errors or modeling assumptions. He calls for continued observation and cautions against premature conclusions. The debate continues. The data remains ambiguous, and the object fades into the outer solar system, carrying its secrets with it. March 2026 approaches, and with it the final opportunity to study 3I Atlas at close range. The object will pass within 1.2 astronomical units of Jupiter, close enough that gravitational perturbations should be measurable, and close enough that Jupiter's moons might offer observation platforms. NASA's JUICE spacecraft, the Jupiter Icy Moons Explorer, is in transit to the Jovian system, scheduled to arrive in 2031. But in March 2026, JUICE is still en route, positioned far enough from Earth that its instruments might catch a glimpse of 3I Atlas as the interstellar visitor passes through the region. Mission planners assess the geometry. JUICE's trajectory will not bring it close to the object, but long-range observations are possible if the spacecraft's instruments are redirected. Commands are prepared. JUICE's cameras and spectrometers are programmed to target the expected coordinates of 3I Atlas during the March flyby. The observations will be brief and distant, but they will offer an independent data set, free from Earth's atmospheric interference and using instruments designed for detecting faint objects in the outer solar system. The Juno spacecraft, already in orbit around Jupiter, is also considered. Juno's mission focuses on studying Jupiter's atmosphere and magnetic field, but its instruments could potentially observe 3I Atlas if the object passes through the right part of the sky. However, Juno's orbit is highly elliptical, carrying it close to Jupiter's poles and far from the equatorial plane, where interstellar visitors are more likely to appear. The geometry is unfavorable, but mission scientists include the opportunity in their planning. On March 12, 2026, 3I Atlas reaches its closest approach to Jupiter, passing at a distance of roughly 180 million kilometers. This is not close by planetary standards. Earth is closer to Mars at opposition, but it is close enough for Jupiter's gravity to affect the object's trajectory measurably, bending its path slightly and accelerating it as it swings past the giant planet. Ground-based telescopes track the encounter. Astrometric measurements, tracking the object's position against background stars, are precise enough to detect the gravitational deflection. If the mass of 3I Atlas is truly 33 billion tons, the deflection should match the predicted value calculated from orbital mechanics. If the mass is lower, the deflection will be smaller. The encounter offers a rare chance to cross-check the earlier mass estimate with independent data. The results arrive in late March, after weeks of data analysis. The gravitational deflection is consistent with a mass of approximately 30 to 35 billion tons. Not exactly 33 billion, but close enough that the earlier estimate is confirmed within observational uncertainty. The mass anomaly is real. The object is far denser than any known comet. This confirmation shifts the debate. What was a puzzling measurement based on the Mars flyby is now a reproducible result. Two independent gravitational measurements, separated by 5 months and involving different planetary encounters, agree. 3I Atlas is heavy. Too heavy. The implications are stark. If the object is 1.5 kilometers in diameter, as photometry suggests, and 33 billion tons in mass, then its density is approximately 8,000 kilograms per cubic meter. This is denser than rock, denser than most meteorites. It is consistent with solid iron or nickel-iron alloy, the kind of material found in the metallic cores of differentiated asteroids. But interstellar comets should not be metallic cores. They should be icy bodies, loosely aggregated, with densities far lower than rock. The density of 3I Atlas suggests it is either not a comet at all, or it is a comet with a massive metallic core hidden beneath a thin shell of ice. The question becomes, how would such an object form naturally? One hypothesis involves planetary collisions in another star system. If a rocky planet with a differentiated iron core were struck by another massive body, fragments of the core could be ejected into space. These fragments, iron-rich and dense, might acquire thin coatings of ice as they pass through the outer regions of their home system, then be ejected into interstellar space by gravitational interactions with giant planets. Such fragments would be rare, but not impossible. The galaxy is old, and violent collisions have occurred countless times across billions of years. If even a small fraction of ejected core material survives to become interstellar wanderers, then occasionally one might pass through our solar system. But this hypothesis requires stacking improbabilities. First, a planetary collision violent enough to eject core material. Second, that material acquiring an ice coating. Third, it being ejected from its home system. Fourth, it traveling through interstellar space for potentially millions of years. Fifth, it arriving at our solar system on a trajectory that brings it close to Mars, the Sun, and Jupiter. Each step is possible. Together, they form a chain of coincidences that strains plausibility. The alternative is simpler in some ways, more complex in others. If 3I Atlas is artificial, the density makes sense. A spacecraft would be built from metals and alloys, with structural components far denser than ice. The ice coating would be deliberate camouflage or radiation shielding, not primordial material. The mass would reflect engineering choices, not accidental formation. But accepting this alternative requires accepting that interstellar travel is not only possible, but has been achieved by another civilization, and that such a civilization has sent probes to our solar system. This is the extraordinary claim that demands extraordinary evidence. The Jupiter encounter provides no smoking gun. The gravitational measurements confirm the mass, but cannot determine composition directly. They tell us the object is heavy, not what it is made of. To know composition requires spectroscopy of the solid surface, not just the coma, and that requires resolution and proximity that current instruments cannot achieve from Earth. JUICE's observations, when they are finally transmitted back to Earth in April 2026, add little new information. The spacecraft's cameras capture a faint point of light at the expected location. The spectrometers detect a weak coma, still outgassing, faintly despite being nearly 800 million kilometers from the Sun. The observations confirm the object's existence and position, but provide no chemical details that ground-based telescopes have not already recorded. Juno, as predicted, has no useful geometry for observation. The spacecraft is on the wrong side of Jupiter during the March encounter, unable to point its instruments at the interstellar visitor. The opportunity is missed, and 3I Atlas continues outward, accelerating slightly from Jupiter's gravitational assist, gaining speed as it heads toward the outer solar system and eventually beyond. By April 2026, the object has faded below the detection limit of all but the most powerful telescopes. Observations become sporadic, then cease entirely. The last confirmed detection is logged on April 28 by the Keck Observatory in Hawaii, a faint smudge barely distinguishable from background noise. After that, silence. 3I Atlas has left the observable region of the solar system. It will continue outward, crossing the orbits of Saturn, Uranus, Neptune over the coming years, but by then it will be far too faint to detect. Within a decade, it will pass beyond the heliopause, the boundary where the sun's influence fades and interstellar space begins. And then it will be gone, another wanderer in the vast dark between stars. Humanity will not see it again, unless it returns. When an object vanishes beyond the limits of detection, all that remains is the data. Photographs, spectra, orbital calculations, measurements accumulated over months of observation. These become the permanent record, the foundation for all future analysis and debate. For 3I Atlas, the data is extensive but incomplete. The object was observed for approximately 10 months, from late May 2025 through April 2026. During that time, dozens of telescopes and spacecraft contributed measurements. The James Webb Space Telescope captured detailed spectra. The Very Large Telescope detected nickel emissions. Mars orbiters imaged the object at close range. Ground-based networks tracked its position nightly. And yet, for all this effort, fundamental questions remain unanswered. The chemistry is partially understood. The early dominance of carbon dioxide has been documented and analyzed. The shift toward water vapor during and after perihelion has been observed. The persistent nickel emission without corresponding iron has been recorded but not explained. Each measurement is solid, reproducible, and strange. The mass is confirmed by two independent gravitational measurements, both yielding values near 33 billion tons. The density implied by this mass is incompatible with normal cometary composition. Either the size estimate is wrong, which seems unlikely given multiple photometric observations, or the object contains material far denser than ice and rock. The trajectory is precisely known, mapped to high accuracy by months of astrometric data. The path through the solar system, passing close to Mars, the Sun, and Jupiter, remains statistically improbable for a random interstellar visitor. Whether this improbability is evidence of intent or simply an unusual coincidence depends on one's interpretation. And the occultation timing, the narrow observation windows, the rapid dimming after perihelion, all of these elements contribute to a pattern that is either a sequence of unlucky breaks for astronomers or a deliberate limitation on how much could be learned. In May 2026, a comprehensive review paper is published in the Astrophysical Journal, co-authored by 17 researchers from 9 institutions. The paper is titled Physical and Chemical Characterization of Interstellar Object 3I Atlas, Observations and Anomalies. It is cautious, technical, and thorough. The abstract summarizes the findings: unusual chemical composition, anomalous mass-to-size ratio, statistically improbable trajectory, and unresolved nickel emission. The discussion section explores possible natural explanations for each anomaly, acknowledging that none fully account for the observations. The conclusion is carefully worded. 3I Atlas exhibits properties that challenge current models of cometary composition and interstellar object formation. Further observations of similar objects will be necessary to determine whether these properties represent a new class of interstellar visitors or are unique to this individual object. No mention of artificial origins, no speculation about probes or technology. The paper remains within the bounds of conventional scientific discourse, presenting data and analysis without venturing into extraordinary claims. But in the acknowledgements, buried among the standard thanks to funding agencies and telescope time allocation committees, is a single unusual sentence. We acknowledge valuable discussions with researchers in astrobiology and techno-signature studies whose perspectives informed our interpretation of ambiguous results. This is as close as the paper comes to admitting that the possibility of artificial origins has been seriously considered. It is a signal, subtle but deliberate, that the authors are aware of the implications and have not dismissed them out of hand. Avi Loeb, who is not an author on the paper but is thanked in the acknowledgements, publishes a response in his blog. He praises the thoroughness of the analysis and the quality of the data. He also notes what the paper does not say, the hypotheses it explores only implicitly. Science advances, he writes, not only by what we state clearly but by what we allow ourselves to consider possible. Jason Wright publishes a more critical response, arguing that the paper should have been more explicit in rejecting artificial origins if the authors believed natural explanations were sufficient. Ambiguity serves no one, Wright writes. Either the data supports the hypothesis or it doesn't. If it doesn't, say so clearly. If it does, have the courage to state the claim and let it be tested. Both are right in their way. The paper is a product of consensus, of compromise between researchers with different perspectives. Some authors lean toward natural explanations, others are less certain. The final text reflects this tension, presenting findings without forcing conclusions. This is how science often works, not through dramatic revelations and definitive answers, but through gradual accumulation of data, incremental refinements of models, and ongoing debates that slowly converge toward truth. The process is messy, frustrating, and uncertain. It is also the best method humanity has devised for understanding reality. For 3I Atlas, the process is now on hold. The object is gone. No new data will arrive unless another interstellar visitor exhibits similar properties, or unless future missions develop the capability to intercept such objects and study them directly. The Rapid Response mission proposed in November 2025 was never funded. Budget constraints, competing priorities, and the lack of definitive evidence of artificial origins combined to table the project. A feasibility study was completed, confirming that interception was technically possible with existing propulsion technology, but the cost was deemed too high for an uncertain return. Perhaps if the nickel anomaly had been more dramatic, or if the object had transmitted a signal, or if the trajectory had been even more improbable, funding might have materialized. But the evidence, while suggestive, was not conclusive, and space agencies, accountable to taxpayers and governments, cannot justify $100 million missions based on suggestive data alone. So 3I Atlas departs unexamined, its true nature unknown, its secrets intact. The data remains archived and accessible, ready for future researchers to reanalyze as models improve and new interstellar visitors provide comparative data. But for now, in mid-2026, the astronomical community moves on to other questions. The summer brings new comet discoveries, asteroid surveys continue, exoplanet catalogues grow. 3I Atlas becomes a footnote, a curious case study, a reminder that the universe still holds mysteries we are only beginning to encounter. Except for a small group of researchers who cannot let it go. Some mysteries resolve with time. New data arrives, better instruments provide clearer observations, and what seemed inexplicable becomes understood. Other mysteries persist, resistant to resolution, growing more puzzling the longer they are examined. 3I Atlas is the second kind. Throughout the summer and fall of 2026, a handful of researchers continue analyzing the archived data. They are not part of a coordinated effort or funded project. They work in spare time, driven by curiosity and the sense that something important has been overlooked. One team focuses on the rotation period. The 16-hour tumbling rate observed during approach seemed consistent with a natural body, but closer analysis reveals subtle irregularities. The period is not perfectly constant. It varies by a few minutes over the course of weeks, speeding up slightly in September, slowing in October, then stabilizing in December. For a solid, rigid body, the rotation period should be constant, unless external torques are applied. Cometary outgassing can produce torques, the rocket effect altering spin as gas vents preferentially from certain regions. But the outgassing from 3I Atlas was relatively symmetric as far as observations showed. There is no obvious reason for the rotation changes. One researcher suggests thermal expansion and contraction as the object heated near perihelion and cooled afterward. Materials expand when heated, altering the moment of inertia and thus the rotation rate. This is plausible, but the magnitude of the observed changes seems too large for thermal effects alone, unless the object's structure is unusually heterogeneous, or unless something inside the object moved. Redistributing mass internally would change the moment of inertia and alter rotation, just as a figure skater spins faster when pulling their arms inward. If 3I Atlas contains movable components, fuel tanks, instruments, anything not rigidly fixed, then internal motion could explain the rotation variations. This is speculation, of course, but it is speculation that fits the data as well as natural explanations do. Another team re-examines the green emission captured in amateur photographs. They compile dozens of images from September and October, taken by different observers with different equipment. The consistency of the green color across independent observations suggests it is not an artifact of individual cameras or processing techniques. The emission is real. Diatomic carbon remains the leading natural explanation. But when the team models the expected intensity and distribution of C2 emission based on the observed outgassing rates and solar UV flux, they find the predicted emission is dimmer and more diffuse than what appears in the photographs. The observed green is too concentrated, too bright. Could there be an additional emission source? Another molecule contributing to the green color? Or perhaps an energy source beyond solar UV, something internal generating the glow? The team cannot answer definitively. They publish a brief note in a minor journal, documenting the discrepancy and calling for future observations of interstellar objects to include high-resolution spectroscopy of any colored emissions. The note attracts little attention. The nickel anomaly continues to defy explanation. A third team searches through decades of cometary observations, looking for any precedent of nickel emission without iron. They find none. They expand the search to include asteroid spectra, meteor ablation studies, and laboratory experiments on metal sublimation. In every case where nickel appears, iron appears alongside it, typically in equal or greater abundance. 3I Atlas is unique. The selective emission of nickel without iron has no natural analog in the solar system or in laboratory simulations. This does not prove artificial origins, but it eliminates the most straightforward natural explanations. The team considers exotic mineralogy, rare compounds that might bind nickel preferentially over iron. They consult geochemists, materials scientists, metallurgists. The consensus is that such compounds could theoretically exist, but would require very specific formation conditions, unlike anything found in the solar system. If they exist in other star systems, their presence in 3I Atlas would be a major discovery in planetary science, independent of any considerations of artificiality. But discovering exotic mineralogy requires samples. Remote spectroscopy can identify elements and simple molecules, but complex mineral structures are beyond its reach. To confirm the presence of unusual nickel-bearing compounds would require analyzing physical material from the object, and that material is now beyond reach, receding into interstellar space at 137,000 miles per hour. The mass anomaly receives less attention during this period. The measurements are solid, reproducible, and published. The density is too high for a normal comet. This is accepted as fact, even if the explanation remains unclear. Some researchers continue to favor the metallic core hypothesis, arguing that fragmented planetary interiors could account for the density. Others remain skeptical, noting the lack of direct evidence for such cores in observed interstellar objects. The debate is civil but stagnant. Without new data, positions harden. Researchers who favored natural explanations in 2025 still favor them in 2026. Those who lean toward artificial origins remain convinced. The middle ground, the agnostics who acknowledge both possibilities without committing to either, grows slightly as the initial excitement fades and the data is digested. By late 2026, public interest in 3I Atlas has almost entirely evaporated. The media has moved on. Social media discussions have shifted to other topics. Only within specialized astronomy and SETI communities does the object remain a subject of conversation. But within those communities, it is discussed often. Online forums host lengthy threads analyzing every detail of the observations. Amateur astronomers share enhanced versions of their photographs, arguing over whether faint features in the coma represent structure or noise. SETI researchers debate whether the object should be classified as a candidate technosignature, even without confirmed artificial signals. Avi Loeb remains the most prominent advocate for the artificial hypothesis. He gives interviews, writes articles, and lectures on 3I Atlas as a possible example of extraterrestrial technology. He does not claim certainty, always framing his arguments as probabilistic assessments based on available evidence. But his 60% figure becomes shorthand for the debate, a marker of how seriously one takes the possibility. Critics continue to push back. Jason Wright reiterates that low probability is not the same as impossibility, and that nature is full of rare events. He points out that for every anomaly in 3I Atlas, there are counterexamples elsewhere in astronomy: unusual comets, strange asteroids, one-off events that initially seemed inexplicable but eventually received natural explanations. The debate is productive in the sense that it keeps the issue alive, ensuring that 3I Atlas does not fade into complete obscurity, but it is also frustrating, circular, without resolution. The same arguments are repeated in new forums with new participants, but the underlying data remains static. And then in December 2026, something changes. Not new observations of 3I Atlas itself, which is long gone, but a discovery that shifts the context in which the object is understood. The Atlas Survey System, the same network that detected 3I Atlas, identifies another interstellar visitor. The object is designated 4I Atlas, the fourth confirmed interstellar object. Initial observations show it is approaching the inner solar system on a trajectory similar to 3I Atlas, though from a different direction. The orbit will bring it close to Earth in early 2027. Astronomers mobilize immediately. Telescopes are scheduled, spectroscopy begins, and within weeks, the first results arrive. 4I Atlas exhibits a carbon dioxide-dominated coma. Its trajectory passes unusually close to Earth, Mars, and the Sun. Preliminary mass estimates suggest high density for its apparent size. The pattern is repeating. The detection of 4I Atlas in December 2026 is both a scientific opportunity and a confirmation of fears. If two interstellar objects exhibit similar anomalies, the likelihood that both are random natural occurrences diminishes. Coincidences happen, but repeated coincidences demand explanation. The initial observations of 4I Atlas are hurried and incomplete. The object is faint, still far from the Sun, and winter weather in the Northern Hemisphere limits observation opportunities. But even early spectra show the now familiar signature: carbon dioxide dominating the coma, water vapor present but secondary. The chemistry of 4I Atlas matches the early chemistry of 3I Atlas. Not identical, but close enough that the similarity is striking. The ratio is not quite 95% CO2, more like 80%, but still far, higher than any solar system comet. The pattern holds. News spreads quickly through the astronomical community. Researchers who studied 3I Atlas immediately begin comparing the two objects. The trajectories are analyzed, the approach angles plotted, the orbital parameters compared. Both objects enter the solar system on retrograde orbits. Both pass close to multiple major bodies. Both arrive on paths that optimize observation opportunities for anyone aboard. The statistical argument strengthens. One interstellar visitor with an unusual trajectory might be chance. Two suggests pattern. If natural interstellar objects arrive randomly, their trajectories should be randomly distributed. The fact that 2 out of 4 confirmed interstellar visitors, Oumuamua and 3I Atlas, now 4I Atlas, exhibit similar orbital characteristics is improbable. Researchers calculate updated odds. The probability that 2 random interstellar visitors would independently follow such similar paths through the solar system is estimated at roughly 1 in several thousand. Not impossible, but uncomfortable. Avi Loeb, in a blog post published on December 28, 2026, raises his assessment. He now estimates a 70% probability that both 3I Atlas and 4I Atlas are artificial. The repetition of anomalies across independent objects, he argues, cannot be easily dismissed as coincidence. Either interstellar comets are fundamentally different from what we expected, with formation and composition unlike anything in our solar system, or at least some interstellar visitors are not comets at all. Jason Wright responds more cautiously. He acknowledges that the similarities between 3I Atlas and 4I Atlas are intriguing and warrant careful study. But he emphasizes that 2 objects is still a very small sample size. With only 4 confirmed interstellar visitors total, patterns can emerge by chance. He calls for observation of more interstellar objects before drawing firm conclusions about whether the anomalies represent a common class of natural objects or something else. But Wright also shifts his tone slightly. Where previously he dismissed artificial origins as highly unlikely, he now describes them as worth investigating. The evidence is not conclusive, he maintains, but it is no longer dismissible. The scientific method requires following the data wherever it leads, and the data is leading toward questions that cannot be answered with traditional comet science alone. Throughout January 2027, observations of 4I Atlas intensify. The object brightens as it approaches the Sun, and weather improves, allowing more consistent observation. Spectra are collected by JWST, Hubble, VLT, and a network of ground-based telescopes. Photometry tracks the rotation and brightness. Orbital measurements refine the trajectory, and the anomalies persist. Nickel emission is detected, weak at first, but growing stronger as the object heats. No corresponding iron appears in the spectra. The selective emission is repeating, just as it did with 3I Atlas. The mass estimates are preliminary, but early calculations based on orbital perturbations suggest high density, similar to what was observed for 3I Atlas. The object appears to be another heavy visitor, far denser than ice and rock should allow. The green glow appears in amateur photographs. The color is vivid, concentrated near the nucleus, matching the appearance of 3I Atlas in September 2025. The consistency is eerie. 2 objects arriving from different directions in interstellar space, exhibiting the same unusual emission. By February 2027, the astronomical community is divided into 3 camps. The first camp maintains that natural explanations remain viable. Perhaps interstellar comets from certain types of star systems carry unusual chemistry and structure. Perhaps we have simply been unlucky, observing only the strange members of a diverse population. More data is needed before extraordinary conclusions are justified. The second camp argues that the accumulation of repeated anomalies across multiple objects shifts the burden of proof. Natural explanations are becoming increasingly contrived, requiring stacked coincidences and exotic conditions. The simpler hypothesis, Occam's razor suggests, is that at least some interstellar visitors are not natural. The third camp remains agnostic, acknowledging the strangeness of the observations, but unwilling to commit to either natural or artificial interpretations without definitive evidence. This camp calls for mission proposals, for intercept spacecraft, for close-range study that can resolve ambiguities impossible to address from Earth-based observations. All 3 camps agree on one point. 4I Atlas must be studied as thoroughly as possible. The object will reach perihelion in April 2027, offering a brief window for intensive observation before it too disappears into the outer solar system. Unlike 3I Atlas, which became occulted behind the Sun, 4I Atlas's geometry allows continuous observation through perihelion. There will be no gaps, no missing data. Whatever secrets 4I Atlas carries, humanity will have every opportunity to uncover them. When it reappears in December, will it return as predicted, or vanish forever? The question hangs over the coming months as preparations for 4I Atlas observation reach a fever pitch. Telescope time is allocated months in advance. Mission proposals are drafted for rapid response spacecraft, though funding remains uncertain. The world watches, not with the casual interest of 2025, but with growing awareness that something unprecedented may be unfolding. and somewhere in the dark between stars, 3I Atlas continues its journey, carrying whatever it is, comet, probe, or something else entirely, beyond the reach of human instruments, into a future we cannot observe.